So we know for this case, this is also what? P. Now, let me go into the extended. You all don't do anything, okay? Stay there. Don't move. In fact, I cannot say y is equal to 0. Or, okay, for this case, bear with me, okay? I should not, but okay, bear with me. Both ends are pinned, right? Both ends are pinned. Okay, so for this case, moment is equal to 0. On the other end, moment is also equal to 0. Okay, so for this side, x is equal to 0, y is equal to 0. For this case, x is equal to 0, y is equal to 0 before buckling. Okay, so that's our P. Now, I want you now to view it from a different plane. We are going to view this from a different plane. Okay. So imagine what we see over here, and we're going to deal with a different plane. Okay. So the plane that we are going to deal with now, so same diagram. Okay, same diagram. So now, again, I'll write down our original transformation. And I want you to talk among yourself. So the plane that we are going to look at now, this is going to be our y, right-hand rule. Someone want to mean z. Okay, so this is our yz. Okay, using right-hand rule yz plane. And then this is rotation about x. Okay, I'm now going to draw point B. So point B looks like this. As you mentioned, it's going through a pin. And then this will extend itself and this is our point A. So probably we have something else over here to stop it from coming out. So this is, what type of shear is this? Double what? Yes or no? Do not forget whatever Dr. Koshi teach you guys. Do not forget. Right. Point A, what is it? Now, if plotted at point A, point B. Point B cannot rotate at all. So moment at point B is now not equal to what? 0. You see that now? So now this is what? Now, when that's the case, I'm going to draw A. What are the forces? A it can be either coming down or it can either be going what? Up. Okay. So what is acting on A? Holy crap. Is going to be your what? FADY is going to be your FAC is going to be your FAB. So these are the forces either going down or coming up. I'm not bothered to label that. It's either coming down or going up. Question for you at point A. Okay. Now I'll give you a different question. If we have a P coming down here, let's say this is the overall resultant P. How will the structure deform? How will the structure deform? The structure now, maybe today I change. I don't want to always on the to the left. I go to the right. No, I don't always go to the left. I always go to the right. Now to the left. So now, this is how the structure will deform. Yes or no? Because there's no forces preventing it from going where? Yeah? Again, there's no forces preventing going from where? Yeah? So when that's the case, what's on top? Anyone? Because moment at point A is equal to what? Be very clear with this. But most of the time, when you go to industry, when you look at the structure, there is no what? At point A, it is P. At point B, it is what? X. We train you wrongly. We give you too much information. Ladies and gentlemen, this is real engineering work. You observe, you apply the boundary condition, you have to know what are the critical conditions. I.e., what do we look at regarding the fixed state? We hunt for the what? Moment. The next thing we do, if we're not sure, we hunt for the what? Deflection. Clear? So by looking at the deflection, by looking how the structure will deflect, is it free? Our students arguing against it. Now, question. Now I will ask you a question to see whether can you answer. Then why is the case over here, right? It is pin. What makes it pin at point A when we view the XY plane? Can you ask yourself? And the structure move. Repeat again. At point A now, when you view the structure move left to right. Yes or no? The answer is no. Why no? Why no? Because you have what? FADX and FADX doing what? Clear? You see that? Well, for down here, what do you see? For down here, is there any left and right reaction forces? Over here, because over here, okay, over here, if this thing were to buckle, right, over here, if this thing were to buckle, it can only buckle in this direction. I.e., the FAB will still be in line in the axial direction. That's where we don't consider it as what? Now the homework becomes just give you a picture of what again I just so for the term test, this is what will happen. You will see the structure before. But I will make condition different. But I can't give you a structure like the Eiffel Tower. Within 2.5 hours, analyze where is different buffer. I can't do it. Okay, so I will tell you, hey, can you test which plane is likely to what? Buffer. You have to do it. You have to be able to what? Analyze. Be clear? Okay, now let's start analyzing it. So for this case, so now some of you ask me, Eugene, where did those numbers come from? Okay, so my bad. So from materials handbook, for L2 steel, okay, the Young's modulus is equal to 200 times 10 to the power 9 Pascal. Okay, and the stress yield is equal to 703 times 10 to the power 6 Pascal. Now, this value, my bad, there's one example. Some of you asked me where did that values come from. Okay, so this will be provided in the question. In the real engineering world, I don't provide you with the question. What do? You don't Google. You look at where? Your materials handbook. Okay. Now, we are given that the factor of safety is equal to what? Is equal to 2. So immediately we know that the factor of safety is equal to PCR over what? T. Okay. And this will be equal to pi squared EI over LE squared. Okay. Now, to check, we have to ensure that the critical stress is equal to PCR divided by A. And to check, we have to ensure that this has to be less than 703 times 10 to the power 6 Pascal. Okay. So let's check. Okay. So now going back to the question again, I will copy the diagram and we bring it down here. Okay, I'll bring down here. So we know that this over here, this is our X, Y, and this is our rotation about Z. And given to us, rod AB, yes. Can you wait? When you solve it, you can see it better. Okay. So over here, AB is what? AB is a rod. Okay. AB down here. Now it is our rod. Okay. So from here, because it's a rod and we have a diameter, and the diameter is equal to 50 millimeters. Okay. So if we have what we have now is we have a what? This is our cross section. When it's a rod, we are really, really lucky. Okay, when it's round, why are we lucky? Okay, so if we were to view this, okay, in a different plane now, if we were to view this, so this direction is our YY, And over here, horizontally, is our what? ZZ. We are lucky in the context that IYY is equal to IZZ, okay, which is equal to pi over 4 R what? And it's the same because it is a what? It is a rod. Are we clear? So over here, this problem don't have a dilemma to tell you what is a wing or which is a Z. Matter, the XX and YY are going to be the same. IXX and Y. Sorry, IYY and IZZ. In that context, have a fantastic weekend. I'll carry on again next week.